Open, please.
I'm sorry.
There is no problem. There is problem. There was a last page of my presentation. All is good. The most important information I talk for my colleagues. Thank you so much. Thank you so much. The competitive WAIC analysis has empirically confirmed the digital transformation must be accompanied by the proactive development of human capital, competencies, and organizational learning based of analysis of the labor market, corporate digital strategies, and educational trends for dimensional competency model has been developed as a fundamental reference for higher education institutions aiming to adapt to high school. Meine Kollegen, I think that is enough of my time to talk about my article together with my colleagues. Thank you so much for attention. I,
Thank you.
I
Thank you
hope
very much
that
for your report.
I hope that my article was interesting for you.
Dear colleagues, maybe you have some questions, please. No questions. Thank you, Helena, for your report. And the next report is approach to
Thank you so much
the
for attention.
of information technology for ACG, electrocardiographic analysis, to evaluate quality of life in smart cities. Authors are Andris Verstyuk, Uliana Polevana, Lubomir Musi, Olga Musi, and Roman Butsi. So please, dear speakers.
Good morning. Could you see my presentation?
Yes, you can see your presentation. Please, you may
Thank you.
start.
My name is Uliana Polevana. The title of the research review of approaches to the development of information technology for electrocardiographic analysis to evaluate quality of life in smart cities. The paper analyzed modern approaches to assessing quality of life in smart cities with special attention to healthcare and electrocardiogram signal modeling. A literature review, 136 papers, Web of Science database, shows increasing global interest since 2018. Over the past 8 years, the number of publications on the topic has increased more than 3 times. Main thematics areas: environmental sciences, engineering, computer science, urban studies. Modern smart cities aim to improve the quality of life of their citizens by leveraging innovative digital technologies like artificial intelligence, big data, Internet of Things, integrated transportation systems, smart energy management, infrastructure for health and public safety, sustainable development and environmental monitoring, enhanced citizen participation through crowdsourcing and digital platforms, and personalized health monitoring models. Approaches to quality of life evaluation, BTOPSIS method, enhanced life satisfaction evaluation allowing for incomplete or fuzzy survey data. Smart C method combines cognitive mapping and chocolate integrals for complex multi-criteria CT assessment. Analytical hierarchical process plus entropy and plus improved TOPSIS. Balanced evaluation of urban energy internet maturity. Use of artificial intelligence and machine learning for decision support in urban planning, environmental monitoring, energy management, public health, and drones plus Internet of Things, efficient real-time data collection in cities. Electrocardiographic signals analyzes model for health monitoring. Electrocardiographic signals reflect key health status indicators important for quality of life. The paper proposes a mathematical model. Electrocardiographic is treated as a cyclic discrete random process. A time rate function is used to analyze amplitude plus time variations of peaks like P, Q, R, S, T. Traditional electrocardiographic monitoring often focuses on RR intervals only. This model enhanced in diagnosis accuracy by considering all electrocardiographic peaks, differing between regular and irregular rhythms. Practical testing, like shown effective for detecting arrhythms and early cardiovascular anomalies, can be integrated into smart city infrastructure like wearable devices, mobile apps. Um, Based on the conducting analysis of publications on modeling and classification of electrocardiographic signals, we proposed a model of temporal rhythm function considering extreme amplitude values of electrocardiographic signals characteristics waves. For a quantitative description of the function, a statistical processing method is applied that allows calculations of the following statistical parameters. You can see these parameters on the slide, please. In practical application, we analyzed electrocardiographic signals under conditions of normal cardiac functions and in patients with extrasystole using the cyclic discrete random process model with a time rate function that incorporates amplitude values of characteristic electrocardiogram peaks. Figure 19 provides a graphical representation of a healthy patient's electrocardiographic signals. The time function of the rhythm taking into account the amplitude values of the characteristic peaks of electrocardiographic signals is shown in the picture. In modern smart cities where wireless sensor network and edge computing technologies are already implemented, this model can be easily integrated in the existing infrastructure with minimal additional investment. Moreover, using this model for cardiac activity monitoring can be part of a broader smart health strategy, with also encompasses analyzing physical activity, air quality, and other factors affecting the cardiovascular system. A model of a cyclic discrete random process for electrocardiographic analysis has been developed. Takes into account not only the RR interval but all main peaks P, Q, R, S, T. Mathematically incorporates both the temporal and amplitude structure of the signal, enables early detection of cardiac pathologies, arrhythmias, extrasystoles. This is a well-structured and innovative study that bridges two important domains: urban quality of life monitoring and biomedical signals analysis within smart city infrastructures. The electrocardiographic model presented has potential for enabling personalized health monitoring, improving preventive health care, reducing public health system burdens. Future direction could include testing on larger, more diverse urban population, addressing interoperability and ethical concerns, exploring integration with multi-sensor health platforms in smart cities. Okay, thank you for attention.
Thank you for your report. Dear colleagues, any questions, please?
Yes, I have a question.
Please.
How does your model differ from the classical time function of rhythm?
Thank you. Our model takes into account the extreme amplitude values of each wave, P, Q, R, S, and T, determines the time intervals between peaks of the same type of waves in adjacent cardiac cycles, and provides detailed information on the rhythmic characteristic of each type of wave.
Thank you. And one more. What are the most active scientific fields in the study of quality of life in smart cities?
Thank you. The most active research fields are environmental sciences like engineering, computer science, science and technology, and urban studies. This is confirmed by an analysis of publication in Web of Science.
Thank you.
Thank you for question.
Any other questions? No questions. So thank you for your report. And the next report is Method and Computer Tool for Fast Prediction of Computer Network Traffic Load Level, authored by Mykola Khustivsky, Lilia Khustivska, and Irina Dedi. So please.
One minute. Dear colleagues, I'm glad to present you a report on the topic method and computer tool for fast prediction of computer network traffic load level. The authors are Mykola Khustivsky, Lilia Khustivska, and Irina Dedi. One of the key parameters of a computer network is traffic, which plays an important role in the process of assessing user activity, monitoring network operation, as well as analyzing its functioning. Predicting network traffic load levels in time-space is one of the methods of avoid congestion, which allows to increase the effectiveness of a network resource use and optimize its performance. For this purpose, various mathematical models and computational methods are used. Among the most well-known traffic models, one can distinguish the Poisson distribution, Markov processes, recovery processes, and phase recovery processes of IPP models. Modulated Markov field model, autoregressive models, stationary processes, fractal Brownian motion, and periodically correlated stochastic process. Based on the models, various computational methods and computer tools have been created for analyzing traffic data in order to predict its load. However, all of these models, with the exception of the periodically correlated stochastic process, do not take into account the relationship between traffic values in different daily periods, which allows tracking the dynamics of traffic change in time-space. This is especially important for network load for nesting tasks. A graphical representation of computer network traffic registered for 7 days within the park complex residential complex is presented in figure 1. The model of network traffic load data behavior presented as a predictive variability and also provides the use of methods and algorithms to study their relationship using the following expression 1. The network traffic data model expression 1 provides extensive processing and analysis capable including synthase, filtering, and component processing to obtain quantitative and informative indicators. These indicators reflect the level of motion correlation of the amplitude time characteristic of traffic at the different times of the day. Studying the level of stochasticity of mutual correlation between network traffic data indicators at different times of the day allows for load forecasting determined in advance the optimal operating models of the network equipment. This helps ensures the stable and high quality provision of communication and information service to network users. Synthase processing of network traffic data is based on the assumption that informative traffic features can be represented as functions with recurring time-dependent characteristic in the form of synthase components. Expression 2. Synthase components allow us to isolate characteristic features of network traffic data, which helps to increase the accuracy of predicting its load in the general context. The sequence of in-phase processing of computer network traffic is presented in figure 5. Figure 3 presents an algorithm of in-phase processing of computer network traffic data. The implemented algorithm figure 3 allows to programmatically create a computer system for synthase processing of network traffic focused on calculating synthase components which act as indicators for effective prediction of computer network traffic load. The guide utility as a component of the MATLAB environment made it possible to programmatically implement a computer system with a graphical interface for predicting computer network traffic. Figure 4. An enlarged fragment of the result of processing computer network traffic data is shown in figure 5. An enlarged fragment of the average synthase 3D components is shown in figure 6. It was found that in the period from 3 a.m. to 5 a.m. and from 5 p.m. to 10 p.m., an increase in the traffic load by customers is observed. At this time, provider should activity the operation of most of the network equipment to avoid overload modes on their functioning. At other times, providers should transfer a significant part of the network equipment to the economical consumption mode in order to save electricity and increase the resource of equipment operation. In order to verify the correctness of the decision made, test the data of unchanged traffic was created with 7 days. The results of its synphase processing were obtained using the implemented program, Figure 7. Based on the processing of stable traffic data, Figure 7, it was ascertained that the in-phase components are at zero level both in the 3D representation and in their averaged form. Therefore, the developed computer system correctly displays on its output the results that correlated with the input. In conclusions, the calculated synphase components of computer network traffic data submit via the periodical correlated stochastic process numerically reflects the future behavior of network load by customers, thereby providing a clear solution to the problem of predicting network traffic load in order to optimize the function of network equipment based on the power of synphase component. Thank you for your attention.
Thank you, dear colleagues. Your questions, if any, please.
I have two questions.
Please.
Good afternoon. First, why does your work focus on studying the covariance of computer network traffic data during in-phase processing, rather than the correlation itself when calculating indicators for predicting future traffic load?
The covariance function operates without averaging with centered network traffic data, which describe not the signal itself, but its variance, which serve as an indicator of load change over time. The correlation function is not able to fully reflect such information since it operates directly with the primary signal, and the process of detecting temporal change is more complicated.
Thank you. And another one question. Do you plan to use the full framework of the energy theory of stochastic signals to study network traffic load data in the future, or have you already applied it?
Currently, one of the well-known methods of energy theory of stochastic signal is used, but in the future, it's planned to use the component method or to process network traffic data and compute the results.
Thank you. That's all from me. Thank you.
Thank you. Maybe another questions, please. No questions. Thank you. And the next report is a mathematic model of electroencephalogram for titanium dioxide neurotoxicity risk assessment, authored by Petro Samulyak, Roman Tkachuk, Pavlo Timkiv, and Oksana Bagrizaets. Please. Please.
Hello, do you see my presentation?
Yes, we can see your presentation. Please, you may start.
Thank you. Good day, everyone. Dear Chairman and conference participants, I am presentation the research result of the topic mathematical model of ERG for titanium dioxide neurotoxicity risk assessment. Nanoscale titanium dioxide is widely used in cosmetic paints, food production, and multiply other industry. Global annual production of pigmentation titanium dioxide is about 9 million tons and the forecast claims that it could reach up to 10 million tons annually in 2025. The main producers of titanium dioxide are China, the USA, and the UAE countries. The studies showed that titanium dioxide nanoparticles can penetrate the blood-brain barrier and they accumulate in the brain, causing oxidative stress, neuroformation, and description of the neurons functionally. In this regard, neurotoxic effects of the visual system is a significant ground in investigation as vision plays a, a crucial role in life quality and overall well-being of a human. Uh, they are standard electrographic method and the diagnostic tools for early detection of toxic. Expert system exists for assessing such effects. The function of such a system is based on the use of mathematical model with corresponding parameter and a coefficient adjusted method. The main difficulty is in determining the model coefficient lies in the limited time for coefficient adjustment for each type electrosignal with needs to minimize it. The last square method for parameter identification.
I'm sorry, but your slides are not changing.
Oh, 1 minute, please. And now,
Yes, now. Please, you may continue.
okay, thank you. The least squares method for a parameter identification is a widely used mathematical approach for fitting data to a polynomial model. In our study, this method was applied determining the coefficient of a third-order polynomial's approximation of ERG signals. Unlike the brute force search method, which Guartis converge but is complicated invented, the least squared methods allow for direction complicated of coefficient by minimalization the sum of squared deviation between observed the model values. Do you see my presentation?
Yes, we
Oh.
see.
Figure 3.
Thank you. Figure 4 graphically illustrated the obtained piecewise polynomial models. Segment 1, 2, and 3 are marked in red, green, and blue colors. Respectively, the points of the curve indicate empirical reference values. It can be seen that smoothie polynomials interpolate the experimental data wells smoothly connected and the boarding points marked by gray lines. The maximum approximation error does not exceed a few percent of the peak amplitude, which confirms the adequacy of the select model for describing the shape of the ERG signals. They compare the efficiency of this method. A study was conducted on a test electrosignal with different numbers, sampling points, and the time for coefficient determination in the MATLAB environment was measured. According to studies, interocular administration of titanium dioxide nanoparticles leads to a signal decrease in both the A wave and the B wave on ERG. For example, in experiments on mice, already on the 7th day after intravitreal administration of titanium dioxide NP, the amplitude of the A wave decreased on average by 50 to 60% and the B wave by 40 to 50% compared to the initial values. In some cases, a significant increase in the latency of the B wave was also noted, which may indicate a slowdown in synaptic transition of the retina. The updated results are as follows. This study presents a comprehensive method for evaluation titanium dioxide nanoparticle neurotoxicity using ERG and analysis. A mathematical model was developed to separate A wave and B wave components, accurate capturing key ERG parameters such as amplitude, latency, and signal direction. A third order polynomial approximation was applied to ERG signals in dark adaptation, ensuring height present with a maximum error under 4.2% of peak amplitude. In vivo experiments showed a wave amplitude dropped by 51 to 63% and B wave by 43 to 52% after titanium dioxide exposure. A 7.6% increase in B wave latency indicates slowed synaptic transmission. The model can support automated system for early neurotoxic detection of titanium dioxide, indefinitely functional change with plus or minus 5% accuracy. Thank you.
Thank you for your report, dear colleagues. Please, you may ask your questions, if any.
I have one question.
Please.
Why did you use the mathematical model of electroretinogram based on the method of third-order phase-wave polynomial approximation?
We used a mathematical model of the electrogram based on piecewise polynomial approximation of the third order because it allows us to accurately describe the complex non-linear shape of the ERG signal. The ERG waveform includes distinct phase such as the A wave and B wave, which have a different dynamics. A single global polynomial or a simple model would not capture this transition and local features effectively. By dividing the signal into physically manageable segments are fitting the separate three orders polynomial to each we can ensure smoothness and the borders and the better represent both amplitude and slope of the signal in each phase. Thank you.
Thank you so much.
Thank you. Maybe another questions? No questions. So the next report is conceptual approach to data transmission for artificial intelligence assisted patient assessment. Authored by Yaroslav Kotov, Evgenia Yavorska, Bogdan Yavorski, and Oksana Dozorska. So please, other speakers present here.
Yeah, hello. Do you hear me?
Yes, we hear you. So you may start, please.
My name is Yaroslav Kotov, and on behalf of my co-author Evgenia Yavorska, I'm pleased to present our work on conceptual approaches to data transmission for AI-assisted patient assessment. In this talk, we will discuss a framework to efficiently capture patient data, feed it into artificial intelligence systems, and deliver the results to clinicians in a structured, usable form. Our goal is to improve the completeness, accuracy, and efficiency of patient assessments by leveraging healthcare data standards and AI. I will outline how patient-generated health data can be captured, standardized, and analyzed by AI to support clinicians. We will discuss the flow of information from patients to an AI system and back to the clinician, highlighting methods to preserve data fidelity and improve efficiency. This talk is based on our thesis work, and it focuses on ensuring that critical patient information is not lost as it travels through digital and AI-driven assessment pipelines. Modern patient assessments generate large volumes of data in various formats. Crucially, over 80% of healthcare data is unstructured text, e.g., patient narratives, notes. This makes it hard to share, analyze, and act on such data. Important details can be buried in free text clinical notes or forms, leading to potential information loss or oversight. These data challenges motivate a need for better transmission methods, ones that structure patient information so that nothing critical falls through the cracks. There are several challenges in transmitting patient information to and from an AI system. First, data heterogeneity. Patients can provide information through narratives, wearables, surveys, etc. These data are unstructured and varied, making it difficult to feed directly into an algorithm. A patient might, for example, describe symptoms in a paragraph of text or upload a photo or wearable device reading. Such inputs don't fit neatly into a database. Second, interoperability. If this information is collected in a proprietary or ad hoc format, it's hard to integrate with the electronic health record, EHR, or share between systems. In fact, many current AI tools operate in silos, unable to pull in or output data in a standard way. While we do have interoperability standards, notably HL7 FHIR, to structure health data, uptake of these standards in AI workflows has been patchy. This means AI systems and hospital IT systems often don't speak the same language. Finally, we must address security and privacy. Patient data transmission must comply with healthcare privacy laws like HIPAA in the US, GDR in Europe. Any solution needs to ensure data is encrypted, access controlled, and meets high integrity standards. These challenges, data heterogeneity, lack of standard adoption, and security concerns, set the stage for our proposed solution. To solve these problems, we designed a structured, secure data pipeline for AI-assisted patient assessments. Patient entry: patients answer a guided digital questionnaire. Their replies are immediately shaped into discrete fields instead of free text. FCHIR conversion: each answer is translated on the fly into HL7 FCHIR resources, observation, condition, etc., giving every system a common data language. Secure handoff: the structured data travels through an encrypted FCHAR API to the AI engine, protected by authentication tokens. AI analysis: the AI model interprets symptoms, assigns risk, or suggests diagnoses. Its output is also encoded as a FHIR diagnostic report with confidence scores. Clinician review: the report drops straight into the EHR so physicians see AI findings in familiar coded fields, no PDFs, no copy paste. Because every hop uses FHIR, interoperability is preserved and nothing is lost in translation. The result is an end-to-end blueprint that seamlessly links patients, AI, and clinicians while meeting security and data quality demands. A key part of our approach is data standardization. We use the HL7 FHIR Fast Healthcare Interoperability Resources framework to structure and encode patient data. FHIR is a modern health data standard designed for electronic exchange of information. By converting patient inputs into FHIR-defined resources, for example, symptoms recorded as structured observation entries, we ensure that data is consistent, machine-readable, and shareable across systems. Standardizing the format means all stakeholders, the AI module, and clinicians are working from the same information, reducing errors and omissions. In short, FHIR helps us preserve the richness of patient data while making it interoperable. This slide illustrates our end-to-end data transmission pipeline for AI-assisted assessment. The process starts with the patient input, 100%, which includes all information the patient provides. Next, a security scrub filters out about 2% of the data, removing sensitive or irrelevant details, leaving approximately 98% of the information to proceed. The data is then transformed into FHIR structured format, with essentially no loss remaining at 98%. The AI analysis stage takes this structured input and produces a synthesized report, condensing roughly another 2% of less important details. The result is a concise output retaining approximately 96% of the original content. Finally, in the clinician review stage, the doctor receives the AI-generated summary, backed by the structured data, effectively almost all of the patient's input, but in a much more digestible form. This pipeline preserves most of the patient's information while enforcing privacy filters and brevity for efficiency. An important technical component is how we will convert unstructured inputs into structured data. We achieve this in two ways. First, if patients answer a standard questionnaire, for example, selecting symptoms from menus, those answers are directly captured as structured data using FHIR questionnaire resources. Second, when patients provide free text descriptions of their condition, we employ natural language processing (NLP). NLP algorithms extract key medical entities, such as symptoms, medications, or durations, from the narrative and map them to standardized codes, e.g., SNOMED, CT, or ICD-10. This dual approach means that whether the input is structured or not, by the time it enters our system, it's converted into a uniform data model. The benefit is a comprehensive coded dataset representing the patient's story, ready for AI analysis without losing nuance. After the data are converted into a uniform FHIR structure, we envision an AI-driven analysis layer that would serve as a virtual clinical assistant. In the proposed workflow, the model would ingest the coded symptoms and history, then condense the narrative into a concise synopsis, stratify risk levels, and suggest differential diagnoses. For instance, the system could highlight high fever persisting 5 days and list the most plausible conditions tied to that pattern. The resulting structured report would be delivered to the physician ahead of the visit, letting the doctor focus on interpretation rather than data triage. Crucially, the AI is intended to augment, not replace, clinical judgment. It organizes facts and flags priorities, while the final decision remains with the clinician. We expect this collaborative model to shorten pre-visit preparation time and reduce the chance that subtle but important details escape notice. By implementing our FHIR-based AI-assisted pipeline, we anticipate a 20% reduction in consultation time from 15 to 12 minutes, alongside a jump in data completeness from roughly 70% to 90% of key patient details available at the point of care. This structured approach preserves nearly all patient inputs in a standardized format, addresses interoperability and privacy concerns, and streamlines clinician workflows without sacrificing quality. Early models suggest it can improve documentation thoroughness and support better decision-making. Next steps will focus on prototyping and real-world pilot studies to validate these gains and refine the system in clinical practice. Thank you for your attention. I am happy to discuss further or answer any questions.
Thank you for your report, dear colleagues. Maybe you have some questions, please, you may ask for them. No questions. So let's move to the next report. Criteria for assessing status to form individual training trajectory, authored by Dmitro Vakulenko, Lyudmila Vakulenko, Svetoslav Ganjuk, and Nadia Ganjuk. So please, you may start your report.
Can I ask, can you on my presentation or not?
Turn on your video presentation, yes?
Yes. Can you on?
Yes, I can.
Please. Dear workshop organizer and participants, I'm Professor Dmitro Vakulenko, and our presentation about criteria for assessing status to form individual training trajectory with telediagnostics platform. Introduction. Modern information technology fast transform healthcare, sports, fitness, and personal health. University years are critical for shaping future professionals. Modern curricula adequate exercise dosing and continuous monitoring are essential. Objective: assess cardiovascular states of 17-22 years old student. Evaluate adequate of gym strength training, lower 20 squeeze in 30 seconds. Use arterial oscillography telediagnostics platform with AI for advanced monitoring. Development background and use cases for integrate telemedicine solution to healthcare, sport, fitness, and personal health. Material and methods. Participants and students doing extracurricular strength training, measurement systolic, diastolic, and blood pressure, heart rate, Robinson and Kerdo index calculated, and recorded arterial oscillogram for future calculation in cloud kernel. Protocol: before load 20 squeeze, barbell for men 40 kg and for women 20 kg, plus 2 minutes rest. Tools: blood pressure monitor with arterial oscillography expert opportunity, telediagnostics platform with AI, and statistical. Means of telediagnostics with AI arterial oscillography. Advanced analysis arterial oscillography. For purpose, the authors develop and unique technology analysis pulsation regarding when measurement arterial oscillography are present, which is implemented to the Oranta AO. Telediagnostics platform with AI. Variable devices which able send raw data, mobile application, calculation kernel, and personal dashboard for monitoring result. Example of use of telediagnostics platform with AI for medical practice, fitness, and research. For prevention, diagnostics and monitoring activity of heart, blood vessels, autonomic and central nervous system, mental disorders. Detection of stress, psychoemotional burnout, and depression. Determine different risk. Assessment of professional fitness, psychoemotional, and status athletes. Determination of functional reserve when conducting Ruffier-Martinet-Kushelevsky test in the pediatric athletes, military, and another. Admission of student to physical education class. Current monitoring of anesthesia during surgery intervention, and monitoring during life in the different cases. Production solution of telediagnostics platform. Available now blood pressure monitors, ECG. Now in the development for patient blood pressure monitor, doctors for monitoring dynamic of movement of limb, position of joint, video camera, smartphone, computer, infrared camera, application, digital stethoscope, and spirometer. telemonitoring innovation. Bring to the telemonitoring flow different devices, supported with IE expert system, individualized system support of inactive, and video consultation with medical profession. Key result: baseline LAGR1 indicators outside of norm in all, 60% had elevated blood pressure value. Robinson index outside safe in 100%, need reduce cardiovascular reserve. Post-load heart rate is larger 77%, blood pressure value modest, larger, limited stroke volume. Arterial oscillography quality in the all 0 excellent to good, pronounced is after disharmony after load. Are developed algorithm and integrated to expert system telediagnostics AI platform this algorithm. Conclusion: students showed a decreased cardiovascular reserve, decrease despite no complaints. 20 squeeze barbell test case, inadequate cardiovascular system response, excessive load. Adaptation relied mainly on heart rate, not blood pressure potential overstrain. Regular blood pressure and heart rate self-monitoring and tailored dosing of exercise advice. R. Identify opportunity application telediagnostics platform plus IE in the sports medicine, fitness, and personal health. Application and future work. Integrate arterial oscillography telediagnostics platform in the routine, sports medicine, fitness, medicine, and personal life. Refine training program based on individual cardiovascular response. Expand sample size, explore static and dynamic load impact. Leverage diagnostics platform plus AI data for AI driven personalized training trajectory. Acknowledges. The authors are grateful to the Ministry of Education and Science of Ukraine for financial project 164-2025, development of personalized telediagnostics platform with artificial intelligence for the doctors and patients, 2025. Head is Dmitrova Kolenko. In the competition, scientific and technological work understates order for scientific and technical development and scientific and technical products. If you have question, welcome. Thank you for your attention.
So please, dear speakers, maybe any questions? No questions. Thank you for your report. And according to our workshop program timetable, I have suggestion to take a short break, if you don't mind, and we'll continue after it. And I'll make appropriate announcement here.
А звуку нема поки що, так?
Ні.
Dear colleagues, let's continue. And I have a proposal to replace next two reports of a valid reasons. If you don't mind, if Roman Pelipets don't mind, I see you're here.
Okay.
Is it possible?
Yes, it's possible. No
Thank
problem.
you so much. So the next report then is computer modeling of the process of shape deviation parameters control and analysis, authored by Andris Verstyuk, Taras Dumeniak, Liliana Gjora, Natalia Yurik, and Yuri Yurik. So please, you may start your report.
Yeah, for sure. So, but just a few minutes to upload our presentation. So do you see it on the screen?
Yes, you can. You may start, please.
It's confirmed. Do you see the presentation on the screen?
Yes, you can see.
So you do. Thanks.
Yes, you may start, please.
So, good morning, dear ladies and gentlemen. So we greatly appreciate you coming here today. And first of all, let me introduce myself. I'm one of the member of the research team from Ternopil Ivan Polui National Technical University. So I'm Liliana Gjora, and I'm a senior lecturer of the Department of Ukrainian and Foreign Languages. So, and I think now we can get started. So, and the topic of our presentation is computer modeling of the process of the shape deviation parameters control and analysis. So to begin with, I would like to emphasize that precise analysis and measurement of the shape deviation are of fundamental importance of precision manufacturing, metrology, and quality control. So over the past few decades, researchers have made significant progress in understanding and qualifying shape deviation, driven by the increasing demands of high precision industry, such as aerospace, automotive, optical, and medical. And as far as us is concerned, in our work, we try to contribute to this growing number of works by presenting new approach to mathematical modeling adapted to the device specifically designed to measure shape deviation. So mathematical modeling is the method of studying processes or phenomena by creating and investigating their mathematical models. Mathematical modeling nowadays is a powerful tool for investigating complex systems, enabling the researchers to provide deeper understanding of processes and phenomena by creating and analyzing their mathematical models. So in our research, the main tool used was MATLAB, which had become the standard for mathematical modeling due to its numerous capabilities and a wide range of functions. MATLAB offers convenient tools for working with matrices, graphical construction of functions, development and debugging of algorithms, and integration with other programming languages. This opportunity provides us and the other researchers with the opportunity to create comprehensive models, which include all aspects of the system under the investigation. So as you can see in this slide, so we investigated the principles of adjacent services. And the following services listed below and concepts which are used as the basis for quantitative assessment of shape deviation. So you can see on this technical drawing that nominal surface is an ideal surface which dimensions and shape corresponds to specified nominal dimensions and nominal shape. Real surface is a surface that limits the body and separates it from the environment. So the nominal and real surface profiles are the line of the intersected of the surface with the plane or given surface. And let us pass to the next slide. And here you can see three formulas which were used during our investigation. The first one represents the cone-shaped coefficient. The second one, barrel-shaped coefficient. And the third corresponds to the saddle shape factor. So 4 main types were used during investigation. They are of elementary shape deviations, that is cone shape, barrel shape, saddle shape, and as you can see at the top, at the bottom of, on the right, deviation of the longitudinal cross-section profile. So the main point we were looking for is an ideal profile. It is the profile one, if it is not, if the assembly technology and manufacturing technology are followed during the roller production, the perfect profile can be achieved. And the main elementary deviation can be evaluated by examining the cross-sectional profile taken at given length of the control shape, of the control sample. So, and now let us have a look at the next slide, where you can see two main criteria, measurement data and real cylinder cross-section. On the left, you can see the graph of the measurement of the shape deviation for the flour milling roller recorded by inductance sensor during one roller rotation. And on the right, you see the cross-section of the cylinder obtained as the result of the measurement. Its deviation from the roundness is affected by both assembly technology and manufacturing technology. And here you can see the result of spectral analysis of the measurement data, again on the right, and on the left, deviation from the given shape. So 3 main lines that together so, and while after our investigation, we can come to the conclusion that applying the demonstrated approach for the analysis of the cylinder cross-sectional profile at different sample lengths, using the data obtained from the above mentioned formulas 1, 2, and 3, we can find 3 coefficients for cone shape, saddle shaped, and barrel-shaped and other shape deviation and defects. The versatility of the approach provides prospects for the application of the developed model, both in laboratory research and industrial standardized processes. So, thank you for your attention. And if you've got any questions, please don't hesitate, you are welcome.
Thank you for your report, dear colleagues. Maybe you have some questions, please.
Yes, I have one question. What goal of calculating and computer modeling of the shape deviations parameters have you achieved?
So you see, the main objective of our research work is to find the coefficients which take into account the correction of the shape deviation parameters in the manufacturing of flour milling rollers.
Thank you.
So thank you ever so much.
Maybe another questions? No questions. So thank you for your report. And the next report is analysis of main square estimation estimator errors on basic frequency or for periodically non-stationary random processes, authored by Igor Yevorsky, Roman Yusufovich, Roman Pelopets, Roman Slepko, Oleg Chak, and Pavlo Semenov. So, please, you may start.
Hello. Hello, everyone. Let me share my screen. Oh, can you see my screen?
Yes, you can.
Okay, let me move somewhere to the right, that part. Hello, everyone. My name is Roman Pelopets. I'm first year PhD student. Today I'm going to present research on analysis of mean square estimated errors of basic frequency for periodically non-stationary random processes. This work has been conducted in collaboration with Igor Yevorsky, Roman Yusufovich, Roman Slepko, Oleg Lichak, and Pavlo Semenov. As shown in equation 1, the periodically non-stationary random processes is represented as a series that includes both cosine and sine terms to model its irregularity and recurrence. This equation provides a stochastic framework for computing hidden periodicities in time series data. The moment function of processes determines the periodic changes in the mean and covariant functions, which can be represented in the form of Fourier series in the following way. Equation 2 represents the mean function and equation 3 represents the covariant functions. The Fourier coefficients of the series in that equations are defined by modulating processes and expressed as in equation 4. Discovering the hidden periodicities using the model of signal as PNRP has been considered in a number of works. The statistical properties of the estimator of the non-stationary period were not analyzed in these investigations, but were briefly characterized. As shown, the biases and the variances of the LS estimators for the mean and covariance functions and the component estimators formed on the basis of their cyclic statistics quickly converge as the realization length draws. As demonstrated, you don't see the number of equations. Let me move somewhere to the right. Yeah. So as demonstrated in equation 5, the LS estimations of the basic frequency for the PNRP mean function can be simplified to finding the maximum points of the squared functional. The equation involves integrating the squared mean function over time to identify the best frequency estimate. The expression shown in equation 6 is a sum of the harmonic components. This formulation allows for the estimation of the fundamental frequency by considering the harmonic series. As shown in equation 9, the time-averaged version of equation 5 leads to the functional, which includes both squared components along with the additional terms that account for higher order smallness as t increases. The next step is to consider the properties of the maximum point of the functional, which are shown in equation 10. This functional can be minimized by solving the nonlinear equation provided in equation 11, yielding the necessary conditions for the optimal estimation. As shown in equation 12, we introduce the normalized deterministic and fluctuation components in equation 10, which are defined by the following functions, where these components represent the fluctuation and deterministic parts of model. Additionally, in equation 13, we decompose the left-hand side of equation 11 into a Taylor expansion around the point omega equal omega 0. As seen in equation 14, we define the sum which involves the normalized deterministic and fluctuation parts. Now, if R of t and tau tends to 0 for all of t in the interval from 0 to p as tau increases, the omega value that produces the maximum of the functional in equation 10 for the Gaussian PNRP is as asymptotically unbiased and consistent estimator for the basic frequency of the mean function, and to a first approximation. Its bias and variance are defined by the formulae. Bias is defined by formula 15, and variance is defined by formula 16. In conclusion, it was shown that LS estimation of the basic frequency for mean and covariance functions of the PNRP can be reduced to searching for maximum points of simplified functional, which are defined by the sums of the powers of the harmonics of the test frequency and its multiples. The values of the maximum points of functional are close to the time average powers of the time changes of related moment function. It was proved that the estimator obtained with such functional for Gaussian PNRP is asymptotically unbiased and consistent if the variance functions tend to zero, with time lag increasing. Formulae for the estimated variances were derived to a first approximation. That's it. Thank you for your attention.
Thank you for your report. Dear colleagues, maybe you have some questions, please ask. No questions, so thank you. And the next report is a comparative study of bug algorithms for robot navigation, authored by Mikhailo Palomar, Mikhailo Strimbitsky, Miroslava Yavorska, and Andrei Palomar. Please, you may start your report.
Good morning. Can you hear me?
Yes, we are.
And can you see my presentation?
Yes, we can see it.
Yes, very well. Good morning. My name is Andrei Palomar, and I'm pleased to present our research titled Comparative Study of Bug Algorithms for Robot Navigation, conducted at Ternopil Ivanpur National Technical University. In this presentation, I will describe our approach to obstacle detection and positioning for mobile robotic platform using laser distance sensors and bug navigation algorithm. Robot navigation involves moving a robot from a start to goal location while avoiding obstacles. This task becomes especially challenging in unknown or dynamic environments. A promising solution in the class of back algorithms inspired by insect behavior, which use simple local rules based on sonar data rather than full global maps. Back algorithms are classified as contact-based and range-based. Contact-based used tactile sensors like bumpers, wide range based use sonar or laser sensors. Contact-based methods are more robust but slower. Range-based approaches are faster but can suffer from sensor noise. Let us briefly review the mathematical model of the robot. Its position is described by vector p, which oriented theta. The distance to the goal, angle to the goal, and the hidden error are calculated using standard formulas. These equations are essential for implementing range-based navigation. The robot switches between two modes, move to goal and follow boundary. These transitions depend on sensor readings such as the proximity to an obstacle or signal intensity. Sensor data include distance measurements and intensity functions with Gaussian noise. Our robotic platform uses a microcontroller-based control system. As shown in this in the distance, as shown in this figure, distance sensors send analog signals to the controller, which determines motor direction and servo position. This architecture allows flexible control of movement and operation. We use sharp infrared sensors which operate via high beam triangulation. The beam reflects of an object, and its angle determines the distance. The internal circuitry converts this into an analog voltage for processing. To achieve high accuracy, we linearize the sensor output using fifth-order polynomial. The conversion from voltage to distance gives a resolution of 0.43 centimeters. This allows precise obstacle detection, which is critical for robot navigation tasks. We use an isosceles right triangle model with 4 infrared sensors to determine the robot's distance and parallelism relative to obstacles. The angle alpha 1 is computed from measurement distances. These geometric methods ensure proper orientation in real time. The work algorithm is as follows. An isosceles right triangle is used to measure the distance and parallelism of the mobile robotic platform to objects. The distance to the object is determined by finding the bisector. After finding the bisector, we find the experimental dynamic distance in motion to the object and compare it with the real one. If the experimental distance differs from the real one, then we determine the angle alpha 1. When performing all angle determinations, we compare it with the actual angle to object 45 degrees. The proposed method of measuring distance and parallelism allows to carry out these operations using a small number of sensors, and also allows to make measurements quite accurately based on the basic characteristics of the sensors. The system demonstrates reliable performance in determining obstacle proximity and robot orientation. The integration of infrared sensors with mathematical modeling enables real-time decisions with relatively low hardware complexity and cost. A mobile robot platform has been developed using laser distance sensors. The autonomous control system can effectively detect obstacles and determine the position and parallelism of the platform relatively to the path. The control software implements a method for dynamic obstacle detection and positioning using discrete digital control. The system calculates coordinates and heating using infrared distance sensors. Experimental results confirm that range-based back algorithms perform contact-based ones as they can avoid obstacles without contact and find shorter or optimal path to the goal. Thank you for your attention. If you have any questions, I will be glad to answer them.
Thank you for your report. So please, dear colleagues, maybe
I
you
have a
have
question.
some questions.
First of all, what are the potential application areas for such robotic platforms, and what do you see the next step in improving the control system of robotic platform? Please.
This type of robotic platform can be applied in various fields, such as defense, for example. First of all, it's very important nowadays, and For example, for autonomous surveillance, for smart logistics, of course, for maybe autonomous taxi systems in the future, in some warehouse automation, and even such and rescue operation in hazardous environments. And if we talk about next step, one promising direction is to integrate computer vision and machine learning techniques. This would allow the platform to better recognize and classify objects and make more intelligent navigation decision, especially in complex or dynamic environments.
And one question, where and how experiments with the robotic platform are conducted? What about this?
Thank you for the question. The experimental studies were conducted in the Information Technologies and Signal Processing Research Laboratory at the Ternopil Ivanopoly National Technical University. And we developed a working prototype and used a modular track to simulate various navigation scenarios.
Okay, thank you.
Thank you.
Thank you. Maybe another questions? No questions. So thank you for your report. And the next report is on the deployment of an open source digital learning ecosystem, authored by Grigory Gabrusov, Vasil Oleksiuk, Pavlo Chopek, and Irina Gabrusova.
Can I share screen? Do you see my presentation?
Yes, we can, please. You may start.
Thank you. My name is Grigory Gabrusov, and I'd like to share you our experience in creating and testing a digital learning ecosystem. The main idea was to build a free, accessible, and effective system for teaching mathematics to technical students. Today, education is going digital very quickly. The COVID pandemic, the war in Ukraine has made online education not just a trend, but a necessity. Also, official documents from the Ministry of Education in Ukraine clearly stress the need for digital transformation in education. This means we need more than just online lessons. We need full digital ecosystem that combine tools for learning, visualization, and assessment. So at the High Mathematics Department, we decided to explore how we can digitally transform the process of learning mathematics. We also involved researchers from Ternopil Vladimir Hnatyuk National Pedagogical University and the Institute for Digitalization of Education of the National Academy of Educational Science of Ukraine. Since most Ukrainian universities have limited budgets and commercial software is often expensive, we focused on open source solutions. We choose to improve our existing system at Tutor by adding open source bus tools. So our ecosystem has three key components. First component is a tutor, well you all know this is the learning management system. It lets teachers update materials, conduct tests, run online consultation, and record lectures. It works great as a central navigation hub of our digital learning ecosystem. Second component is Sage Math. This is open source math platform. It helps students do calculations, plot graphs, and solve equations directly in the web browser. It can be called a free educational alternative to MATLAB. And the third component is GeoGebra. This is free visualization tool. It makes static math diagrams interactive. The students can experiment with formulas and parameters while reading static lecture content. We have already implemented this system in some topics of course high mathematics, such as linear algebra and analytic geometry. So how does it work in practice? Through their personal accounts in a tutor, students can access materials enhanced with GeoGebra. They can complete practical tasks using Jupyter notebooks, run code and calculation using our virtual SageMath server. And the best part, no extra software is needed. Students only need a cell phone, tablet or a laptop with browser and internet access. We haven't yet completed a full statistical study that is planned for next year. But even now, by comparing students who used the new materials with those who didn't, we have noticed that students have become more interested in learning, become more active. Thanks to visualization provided by GeoGebra, students began to understand mathematical concept more deeply. In addition to better understanding of mathematics, students gain new skills in working with modern informational technologies such as Python and Jupyter. So what are the key advantages we see in the proposed learning ecosystem? The entire system is completely free. This is extremely important because today Ukrainian universities are very limited in financial resources. Any university can adapt it to their own needs. This is ensured by the presence of the fully open source code for all products. In addition, all used projects are active and constantly updated. Therefore, our programmers have the opportunity in the future to join the global community of software developers. Thanks to Docker containers, it's easily to install on a PC, in a lab, or on a university server. It is scalable and works on any level. We are excited by the early results and already planning our next steps. We want to extend this system to the full high mathematics course, and we want adapt testing, some adaptive testing features, improve the mobile experience, especially on smartphones, collect, analyze students' progress data, involve our other departments and university, integrate it with other platforms like Moodle. In conclusion, our digital ecosystem based on open source tools really works. It improves learning quality, increase accessibility, and boost students' motivation. Thank you for your attention.
Thank you for your report. Please, dear colleagues, maybe some questions, please ask.
I have a question. First of all, is it better to use MATLAB or MATCAD when studying mathematics? And how difficult is for teacher to master from this system?
I cannot answer what is better, MATLAB or SageMath. For different tasks, someone is better. For teaching, for studying, as for me, SageMath is a more practical choice because licensing for MATLAB or MATCAD or other commercial software is too expensive for Ukrainian universities. And as for me, it is not very difficult to use SageMath by teachers, by students, by anyone, anybody. This is why, because it has good web interface thanks to Jupyter, and it use well-known language, useful language, Python. So it, as for me, it is not very difficult to master Jupyter or Sage Mast. But we can use some short training or mini courses for colleagues if it will be needed.
And one question, can the system be used not only for mathematics, maybe on other?
Yes, any subject, if you need do some calculations, you can use Sage Math or other mathematical programs. In particular, one of the authors, Pavlo Chopik, right now used Sage Math in laboratory work on the physics at the pedagogical university.
Thank you. Thank you for your answer.
Thank you for your questions. Maybe other questions?
Dear colleagues, I'm sorry, I have some technical problems with internet connection. Thank you for your report. Please give me 2 minutes and we'll continue, if you don't mind. Thanks.
Okay.
2 minutes, please.
Конференцию запускает.
Okay, I connected successfully. Thanks for your waiting, and let's continue. The authors of the last 4 reports scheduled for today can be present here now of valid reasons. So I'll turn on their video presentations, if you don't mind. Okay, the next report is automated approach to determining chicken eggs parameters based on their digital images, authored by Igor Konovalenko, Volodymyr Medved, Alexander Shovkun, Katerina Morushchak, Denis Baran, and Bogdan Rusev.
Perimeters based on their digital images. Optical digital control methods and ovoscopy are used in the quality control of chicken eggs. Chicken eggs are investigated in the egg tester ovoscope. Egg tester can be of different designs. An easy-to-use installation of photographing chicken eggs under controlled conditions need to be developed. This research aimed to developing an automated method for determining the geometric dimensions and volume of chicken eggs by processing their images. To conduct this research, an installation was developed, which features a box consisting of the upper one and lower and second parts. During the experiment, chicken eggs were placed on stand 6 in the middle of the chamber. Side walls of the upper and lower parts of the chamber are painted black from inside. Opening 3 with a diameter of 90 millimeters, through which the camera takes photo of the assignment is located on the cover of the upper part. The opening is also painted black from inside. On the inside of the top cover, LED models are located around the opening, which are covered by a light diffusing screen made from white acrylic plastic. At the bottom of the lower part of the chamber too, there is the same number of LED models as on the upper one. The pictures are showing the structure of the chamber. The illumination flux emitted by LEDs located both on the upper and lower parts of the chamber can be adjusted by changing the voltage from 2 separated power sources. Figure shows the output voltage of which can vary in the range of 5 to 12 volts owing to the surface illumination of the specimen studies in the chamber can also vary in the range of 100 to 500 lux. In the source of research, the following parameters were measured. Constant voltage of the LEDs located on the upper and lower parts of the chamber. Illumination of the specimen surface. Chicken eggs were photographed at illumination E of 660 lux. The geometric dimension of studies objects were calculated automatically using the developed algorithms and the mechanical digital caliper, which an accuracy of 0.01 millimeters. A robust image processing algorithms can identify eggs in varying lighting conditions, orientation, and background complexes. The algorithm used in this work is based on classical image processing technique and consists of several major stages: images filtering, image segmentation using thresholds, macroscopical operations, erosions and dilations, object detections and calculation of detected objects' dimensions, height, volume. Laboratory obtained RGB images of X are shown on figure. The initial step is the egg detection process involves images filtering, which aims to reduce the noise and smooth on the images while preserving the essential features like edges and contours of the eggs. A Gaussian filter is applied to the place-care images to remove high-frequency noise. This filter blurs the images, which helps in reducing small artifacts that might be misclassified as spots. After preparation stage, images is segmented. Segmentation is an essential step where the goal is to distinguish the eggs foreground from the background. After segmentation, the binary images may still contain noise, holes, or fragmented egg shapes. To address these, macroscopical operations are applied to clean and consolidate the detected region. In the final binary images, where white pixels represent the object's X and black pixels represent the background, the areas of the object can be computed by counting the numbers of white pixels. These physical attributes of X are essential for various applications ranging from optimization incubation practices to prediction quality and ensuring customer satisfaction. Thus, the study is concentrated on computing geometrical parameters of X, specifically their dimensions and volume. Table 1 summarizing X measurements and allows to compute the results made by proposed images recognition methods with manual measurements. It makes possible to estimate the effectiveness of the developed algorithm. In general, the data summarizes in Table 1 testing for the effectiveness of the developed automated algorithm for detection of the geometric parameters of X. The obtained relative errors for height and width are quite low, which indicates that the method's accuracy is acceptable. A relative error is determining the volume was somewhat larger. This may be due to a more complex algorithm used in the calculation of the volume based on a two-dimensional images. An automated method for determining the geometrical dimension, height, width, and volume of chicken eggs based on processing the digital optical images is developed and tested. A specialized installation for obtaining photo images under controlled lighting conditions and an algorithm for calculation of X parameters are proposed. The research results show a high consistency between the geometric parameters and X determining using the developed automated method and the results of the direct mechanical measurements. The relative error is in determining the height and width and volume of X didn't exceed 3 and 6% respectively. This indicates the effectiveness and acceptable accuracy of the proposed approach for practical implication in quality control system. The results show that the developed installation and images processing algorithms have the potential to create easy-to-use and reproducible system for automated determining the X parameters. This can help increase the productivity of sorting, calibrating, and quality control processes in the poultry industry.
Dear colleagues, I see between the participants the author of a next report, Denis Olyanin. Can you present your report? Okay, his present part can't use microphone. Put in my video presentation. Okay, I'll put on your video presentation now. And please, if any questions on this report, please, dear colleagues, write in chat for next report for Denis Olyanin. So the next report is Transformer Neural Networks in Industry 4.0, authored by Denis Olyanin and Helena Zuper.
Everyone, I'm Denis Olyanin, a PhD student at Ternopil Ivan Palyuin National Technical University, and I'm happy to present the joint work my colleague, candidate of technical science Helena Zuprek, and I have done on transformer neural networks in Industry 4.0. Over the next few minutes, we'll see why self-attention models are rapidly becoming the analytical backbone of smart manufacturing. Our paper asks a simple question: how far can transformers push industrial intelligence? In answering it, we cover three critical application families: unstructured text, such as maintenance notes and system logs;
computer vision quality control, where subtle surface defects must be caught in real time, time series sensor streams, the heartbeat of every Industry 4.0 line. In each domain, we evaluate performance, present case studies, and identify the practical constraints to prevent wide adoption. Transformers were first introduced for language translation, but their power lies in three architectural choices. Self-attention weighs the relevance of every token or pixel or sensor reading to every other, capturing long-range dependencies lost in recurrent neural networks. Parallel processing means an entire sequence is handled at once, giving dramatic speedups over step-by-step models. Positional encodings preserve order so context isn't lost. From this foundation, several variants emerged. Encoder-only BERT for understanding data, decoder-only GPT for generation, and the Vision Transformer, or in short VIT, when images are broken into patch sequences. The same mechanism that translates sentences can therefore flag faint scratches on leather or correlate temperature spikes with vibration drift. Industrial plants generate millions of log lines and freeform maintenance commands every day. Traditional regex parsers can't keep up, but transformers can. T4PDM, a stripped down transformer without usual encoder-decoder steps, rotating machinery failures with 98% accuracy. In benchmark studies, Lockbird pushes precision, recall, and F1 score about 0.9 when separated normally from faulty sequences. A NVIDIA prototype that analyzes DGX server logs locates the root cause log lines with 99.9% accuracy. So an engineer needs only a few seconds to review the highlighted information. Finally, Robert CRF pipeline extracts equipment, fault causes, and remedies from Chinese reports at 0.95 F1 score, a leap over earlier RNN baselines. Factories use cameras to inspect each product, yet detecting a minute crack in a low-resolution image remains difficult. The Vision Transformers, or VITs for short, offers a solution to this problem. On laser sheet inspection, modern VIT outperformed lightweight CNNs, or convolution neural networks, in classifying defective versus normal samples, even with small, lower resolution datasets. Self-attention lets the network look at the entire image context, so it both flags and localizes the exact pixel region of a wrinkle or scratch. Because VITs are pre-trained on massive image libraries, a plant engineer can fine-tune a model for new parts in hours with only a handful of examples. Similar gains appear in PCB crack checks and weld X-ray analysis, where VITs remains robust under changing lighting or camera angles. Modern factories are equipped with numerous IoT sensors that continuously transmit vibration, temperature, and pressure data at kilohertz frequencies. Such self-attention models are especially effective at identifying subtle early indicators of failure within these streams. Transformer adversarial models on multivariate IoT data induce false alarms while catching subtle anomalies others miss. Imagine an LSTM model with transformer encoder raised the accuracy of remaining useful life predictions on real-world equipment datasets, demonstrating that hybrid designs can leverage both local and global patterns. In a recent planned trial, a transformer-based framework lifted product yield from 78 to 89.6% while maintaining near real-time inference at the edge. These studies confirm that transformers are not just accurate, but deployable in latency-sensitive production settings. Transformers currently provide leading-edge performance across all primary 4.0 data streams, text, images, and sensor signals. They consistently exceed 90% precision, identify defect missed by convolutional neural networks, and predict equipment failures several days in advance. Nevertheless, three limitations remain: the quadratic memory requirements of the attention mechanism, the need of transparent reasoning that operators can trust, and the difficulty of deploying large models on low-power edge devices. Ongoing work on sparse attention, model quantization, and visual saliency is addressing these issues. If these challenges are overcome, transformer-based AI is likely to become the central component of fully autonomous, self-optimizing factories. Thank you for listening.
Okay, dear colleagues, reminding you that you may ask your questions in our chat on this topic, on this report. And the next report is multi-parameter hemodynamic monitoring via machine learning, data-driven framework for cardiovascular physiology, authored by Alexander Brick and Oleg Pastov.
Morning, everyone. My name is Alexander Brick, and today I'm presenting a recent study titled Multi-Parameter Hemodynamic Monitoring via Machine Learning, a data-driven framework for cardiovascular physiology, which proposes a novel, non-invasive approach to predict systemic vascular resistance, CVR, using machine learning and physiological data. So let's get started. And first of all, let's start from the problematic. System vascular resistance, or CVR, is crucial for understanding cardiovascular load and vascular health, but it's clinically underused because it depends on measuring central venous pressure, which requires catheterization. That makes CVR impractical in outpatient primary care or wearable settings. This limits early detection and personalized therapy. The core idea is simple. Instead of measuring CVP invasively, we learn to infer it from signal we can easily obtain, like heart rate, stroke volume, and blood pressure patterns. With machine learning, we can detect hidden relationships that conventional formulas overlook. This study used a comprehensive cardiovascular dataset including over 30 features per patient, from blood pressure and flow dynamics to wave morphology. CVR was computed using standard clinical formula as a reference. Then we discretized it in 3 categories to match clinical decision points. Here again, this is our formula. for CDR. Okay, we can move forward. For over 30 signals, the final model uses just 5, all non-invasive and clinically interpretable. These features were selected using permutation importance across models, with weight based on classifier accuracy. This approach balances robustness with clinical transparency. Classifiers used. We tested 4 classifiers with different assumptions, from linear to nonlinear, local to global. This allows a fair evaluation of the complexity needed to predict CDR. All models were trained using only 5 selected non-invasive features. Confusion matrices show that the models rarely confuse low and high CDR. They make errors at the class boundaries, like normal versus high. That reflects true clinical ambiguity. Random forest performed best, showing confident prediction across all classes. So we can see random forest on the bottom right corner. Random forest reached near perfect performance with 99.89% accuracy and F1 score. Even the simpler models performed very well, confirming that CDR is indeed predictable for non-invasive data when the right test features are used. Here is the result once again. As we can see, logical regression is have the lowest results, and the random forest have the higher results. The KNN and CVC have average results. In summary, this study presents a robust, interpretable framework for non-invasive CDR prediction using machine learning. It enables accurate classification using just 5 easily measurable parameters, a breakthrough for safer, smarter cardiovascular care. Future directions include wearable deployment, real-time monitoring, and clinical validation. Thank you for your attention.
Okay, and the last report scheduled for today is telemedicine and psychocorrection, a new paradigm through healthcare data processing innovations, authored by Dmitro Vakulenko and Elena Hevko.
Good morning, everyone, dear colleagues, distinguished members of the Presidium, ladies and gentlemen, esteemed guests. Please allow me to introduce myself. My name is Elena Hevko and I am an Associate Professor PhD at Ternopil Ivan Piliu National Technical University. Today I'd like to present our research. The topic of my presentation is telemedicine and psychocorrection, a new paradigm through healthcare data processing innovations. We propose a novel approach to creating a telemedicine psychorehabilitation system taking into account various methods for assessing stress responses. The methodology is developed based on the RANTOMIS information system. The proposed comprehensive telemedicine system is able to detect stress, control it by tracking stress markers, and simultaneously correct the patient's condition, which makes it effective and convenient in everyday life. Stress disrupts homeostasis and contributes to the development of various somatic and mental illnesses, negatively impacting cognitive brain functions and the state of the cardiovascular system. Accurate and optimized monitoring of stress indicators and the ability to manage them are priority tasks in medicine, yet they remain debatable. The goal of our approach to the timely detection and correction of stress is to create a comprehensive psychorehabilitation telemedicine system based on the general algorithm presented below. There are systems for diagnosing stress based on single indicators, whether laboratory or psychological. We suggest combining subjective and objective mental health assessments in our telemedicine system. Subjective stress assessment can be effectively monitored remotely using interviews and questionnaires. There are two types of stress, acute and chronic, and they can be differentiated using questionnaires. For instance, Cohen's perceived stress scale was used at the beginning of the war in Ukraine for online surveys of Ukrainians. It is advisable to conduct an objective assessment of stress by examining both biochemical markers and physiological responses. Biochemical markers of stress can be detected in blood, urine, sweat, tear fluid, and saliva. We were particularly interested in monitoring salivary cortisol levels as a simple method. In recent years, remote monitoring methods for salivary cortisol levels have been most intensively developed, even using smartphones focusing on biosensor technologies and platforms. There are a number of physiological reactions that are easy to monitor and are informative in stress diagnostics. These include electrodermal activity, change in respiratory rate, heart rate variability, and etc. Heart rate variability is the most frequently studied as it allows for timely detection of increased sympathetic activity associated with stress. This requires analyzing the time domain and frequency domain of heart rate. The signal is typically collected using electrocardiography. However, the complexity of electrode placement and the unwieldiness of the method complicated remote monitoring. Arterial oscillography has emerged as an alternative method which allows assessing these same indicators and several additional ones that are currently being researched. Furthermore, and the software for the Uranta AO information system developed by a team led by Professor Dmitrova Kulenko makes this easy and simple. The aim of this work is to develop methods and algorithms for creating a telemedicine system for comprehensive diagnosis and correction of stress. To achieve this goal, the following tasks have been set. We conducted an experimental study on stress levels using the Uranta AO information system, employing questionnaires and arterial oscillography methodology. Anxiety and depression levels were assessed using the hospital anxiety and depression scale and the state trait anxiety inventory, while neuroticism was assessed using Eisenke's methodology. We surveyed 260 patients. Anxiety in the sample closely correlated with dominant sympathetic activity according to arterial oscillography data. Specifically, over 30% of students demonstrated high levels of neuroticism and anxiety. However, for future studies, we propose using questionnaires for stress detection with a differentiated approach to stress types, chronic or acute. Spectral measures of heart rate variability, such as low frequency power and high frequency power, very closely correlated with the corresponding anxiety level scales. Thus, a negative correlation was observed between HF and anxiety, while a positive one was observed between LF and anxiety. As the stress level increases, LF increases and vice versa. When HF is increased, a person feels calm. In the time domain analysis, the index of tension over regulatory system positively correlated with anxiety level. In the remaining students, activation of SDNN and RMSSD was observed, which indicated the dominance of the parasympathetic nervous system. Based on the above, we proposed a general algorithm for a telemedicine diagnostic system for stress detection, based on arterial oscillogram acquisition and questionnaires that were integrated into the Uranta AO system. An experiment was conducted to study the impact of multimedia calming compositions integrated into the Orantamist telematic system on students experiencing stress. As a result, changes in the spectral and time domain characteristics of heart rate variability were observed. Video images of natural elements played a particularly important role: bubbling water, flickering flames, and forest bird songs. It was experimentally demonstrated that after viewing bubbling water, the stress index significantly decreased, parasympathetic tone was activated, and AGF increased from 48 to 64. Therefore, it was considered appropriate to add a module with multimedia compositions to the diagnostic component of the automated system, functioning as a feedback system. However, for a comprehensive assessment of physiological state, we recommend including in the system not only heart rate variability measured by arterial oscillography, but also the measurement of other stress markers and tracking their changes under the influence of multimedia compositions. Therefore, the system for stress physiotherapy should, in addition to assessing stress reactions using a questionnaire and heart rate variability data from arterial oscillogram analysis, also include monitoring of cortisol in saliva and measurement of other physiological responses. Furthermore, such a system should also include a block of signal selection, primarily via a mobile application, a signal analysis module in a cloud-based computational service, and a therapeutic intervention module for the patient. This intervention module should be selected based on the relevant diagnostic data using a feedback system within the user's personal dashboard. Once the data in the information analysis module has been analyzed, the expert system immediately identifies the results that deviate from the norm and selects a multimedia composition via the feedback system. Such a system will allow for comprehensive, multifaceted assessment of stress levels. Continuous feedback, which is fundamental to the system's operation, will enable individual psychocorrection during diagnosis and the tailoring of specific interventions. The proposed new stress psychocorrection system will open new horizons in psychology, help psychotherapists better study the pathogenesis of stress reactions, and therefore enable their timely detection and effective management. The authors are grateful to the Ministry of Education and Science of Ukraine for financial support of the project development of a personalized telediagnostic platform with artificial intelligence for the doctor and the patient. Hit Dmitro Vakulenko in the competition scientific and technical work on the state order for scientific and technical developments and scientific and technical products. That concludes my presentation. Thank you. Thank you for your attention.
Okay, dear colleagues, all reports scheduled for today were presented. For video presentations on reports of video presentations, you may ask your questions, write your questions on our mail of our conference of this workshop. This is the final time of the CITI International Workshop on Computer Information Technologies in Industry 4.0. All 32 reports were successfully presented. All 32 reports scheduled for this workshop were successfully presented by the authors according to the workshop program. Thus, it can be claimed that the workshop took place. And on behalf of all the workshop organizers, I want to thank you for great work done. I wish you all the best and stay safe. Goodbye. Meet you next year, next workshop.
Okay. Thank you very much. Goodbye. Thank you very much.
Goodbye.